This video is on Unit 1.4, Exponential and Logistic Growth. In the video I'll be talking about how different populations can change over time and the difference in the curves between the exponential and logistic growth. So first we'll look at the exponential growth. Exponential growth is a model that scientists use to describe the change in a population's growth over time. For our example, we're going to use these 10 mice here and watch how their population grows over time. So we're starting at generation 0, and our number of mice, or our n, is 10. We're going to say in the next generation, generation 1, we had 5 mice that were born, but we also had 1 mouse that died. So I'm going to cross that mouse off. So we have a total of, in this case, 14 mice, since 5 were born and 1 died. From that information, we can figure out what's called the growth rate, or R. R equals births minus deaths over n, n being the number of individuals in the population. So in this case, our births were 5, our deaths were 1. We plug those into our equation. The births at 5 minus the deaths at 1 divided by the number in the population to begin with, which was 10, equals our growth rate of 0.4 for this population. So from here on, we're going to assume that our growth rate stays at a steady 0.4, because that is one of the definitions of exponential growth. So if we have 0.4 growth rate on our 14 mice that are currently in the population, we can determine how many mice will be added in the next generation using this equation. D times n, which means the change in the number of mice, divided by d times t, which is the change in the amount of time, equals the rate times the number of mice. So if we put these into our equation, we know that our rate, as I said earlier, never changes. The rate will always be 0.4. Our n from this time is 14, because we're now dealing with 14 mice in the population. So our r times our n value is 0.4 times 14, which means we're going to add 5.6 mice to the population in the next generation. We're going to round that up to 6 for a total of 20 mice. We now have 20 mice in our population. Moving on to generation 3, we're going to stay at the 0.4 growth rate. Now times those 20 mice that are in the population gives us an additional 8 mice for the next generation. We add those in. We use that new 28 as our n value to calculate how many mice will be in the 4th generation. We're going to maintain that 0.4 growth rate times our 28 mice for a total of 11.2 mice added to the population, rounded to 39 total mice. So in just 4 generations, at a growth rate of 0.4, we went from 10 mice to 39 mice. Now if we graphed it out, it would look something like this. From generation 0 to generation 4, a pretty steady increase. Let's say, though, we didn't have those numbers and we wanted instead to figure out how many mice will be in every population. We could use this equation instead. So in this equation, we have n again being the number of organisms in the population. T represents our time, or our generation that we're using. R is still the rate of change, and we're going to use those to figure out how many mice are going to be in the population at any given time. So let's work with the ones we're familiar with already. So the ones we started with was at generation 0, or t equals 0. We had 10 mice in our beginning population, so that 10 goes here for the big N. 1 always stays constant. The 0.4 is our growth rate, which again stays the same because we're always going up a 0.4 growth rate for each generation. And our 0 up here is again from our time, or t equals 0. Now any unit to the 0 power is going to equal 1. So in this case, our n times t equals 10 times 1, or 10. That's what our population was in generation 0. It was 10. Looking at the next one, we've got generation 1. Still, we had started out with 10, so that stays the same. So 10 is the same here. 0.4 growth rate is the same here. This time, though, it's to the first power, because we're in generation 1. Anything to the first power is itself. So in this case, we have 10 times 1.4, or 1 plus 4. 10 times 1.4 equals 14. We had 14 mice in our second generation, so that checks out as well. Generation 2. Still, we had started with 10 mice, so that doesn't change. The 0.4 growth rate still stays the same, so it's 1.4 in the parentheses. But since it's generation 2 is to the second power, you multiply that out, you get about 20 mice, which is what we had in the third generation. Now we could use this to predict how many mice will be in future generations as well. We could predict 30 generations into the future, or 100 generations in the future. When you calculate these out, these get to be some pretty big numbers. Generation 30, we would expect to have around 32,000 mice. In generation 50, this is a typo, should be generation 50, we expect to have around 145 million mice. So you can see in exponential growth that this type of growth rate that never changes really makes the population increase quickly. If we were to graph this out to the 50th generation, you'll see it makes this very distinctive curve. We call this curve that grows exponentially without slowing down a J curve, or sometimes called a hockey stick curve. This is very characteristic of exponential growth. All right, so exponential growth, just to review, our main equation that we're using here is the d over n, or d times n over d times t equals the rate times the number of organisms in the population, and the rate stays steady. Next, we're going to look at a different growth model called logistic growth. For logistic growth, I'm going to use this simulation that's online from a place called NetLogo. And in this simulation, the greens represent the grass in the population, and these little white specks represent the rabbits. Now we're going to let them grow for a little while and see what happens. You want to watch the graph down here in white as I press go. All right, so you can see the green line for the graph increased and then decreased, and then afterwards the red line for the rabbits increased and then decreased. So neither one of these populations was able to continue growing exponentially. Instead, the grass started to grow and then died off because the rabbits were eating it, and then the rabbits started to grow but then died off because the grass was going dead. So if we keep this going for a while, we can see that eventually these two populations begin to level off. And this point of leveling off, it's a little bit of up and down, but pretty much staying in the same range, is called the population's carrying capacity. And this is what logistic growth looks like. So in logistic growth, we've added in this idea of a carrying capacity, and that is represented in the logistic growth equation with this K value here in red. So you'll notice the logistic growth equation is almost identical to the exponential growth equation, except for what I've added in red. And again, the K stands for the carrying capacity. Which is essentially the maximum number of individuals that an environment can hold. So in our little rabbit video, you could see the population leveled off after a while because it reached its carrying capacity. Now let's apply this equation to actual numbers. So what we're going to do is use the equation to determine how many mice again we're going to have after each generation. We're going to assume that our rate of growth is still 0.4, but we've added in this carrying capacity this time of 20. So K equals 20 for these equations. So let's figure out the first one. If our n is 10, the next thing we need to figure out is the Kn over n value. Okay, in this case again, the K was 20. The N is 10. We're going to divide that by N, or 10. We're doing this part of the equation right now. So that's 10 divided by 10, or equal to 1. So K minus N over N equals 1. Now to figure out this whole equation, which is equal to this section here, we need to take that value we just figured out in red, which was 1, times the R, which as I said is 0.4. That's going to be the same throughout, times the N, which in this case is 10. And we multiply that all out. That value equals 4. That means that 4 individuals get added to our population for the next generation. So this is going to be 14, or 4 plus 10. Now we need to find the next step. So again, we're going to take K, which right here, K is still 20, minus N, but our new N is 14, divided by 14 again, or N again, and that value is going to equal 0.4. We take that number again, 0.4, times the N value, which in this case is 14 now, times the rate, which never changes, which is also 0.4. When we multiply all those numbers together, we get a value of 2.24. When we add that to the 14 that we had before, get a total of 16.24. Okay, I'll do one more row. 16.24 is our new N value. So to calculate this value again for our third column, we take 20 minus that 16.24 divided by 16.24. That value equals 0.23. Take 0.23, which is this number, times the N, which remember was 16.24, times the rate, which never changes, which is 0.4, and that value equals 1.5. So we're adding another 1.5 individuals to our population. So our population is now 17.74. Let me fill in these other ones so that we remember where we came from. So you can see that we're moving up much more slowly in this population than we did in the exponential growth model. So the rate is the same. We're still multiplying times 0.4 each time, but because that carrying capacity is taken into account, the increase at each generation is smaller than the one before. Now, different organisms have different ways of dealing with these R and K values because they all want to pass on their attributes to the next generation. So in class, we're going to talk about R selected and K selected values.